The topic for this video is an overview of linear quadratic optimum control. And the outline of this video is that it starts with motivation. We'll talk about why we're interested in studying optimal control. And then we'll look briefly at the method for performing optimal control. Again, like I said, this is an overview video, so we're not going to get into much detail in the derivation of the equations. Finally, I'll provide two examples and then summarize what the video covered. Talking about why we're interested in optimal control, if the pole placement method enables specification of all the closed loop poles, why is that not sufficient? So why are we not content with that method? Why are we interested in an additional method for designing a controller? Well, one big reason is that the designer might not know the best closed loop pole locations. So since that's the starting point of the pole placement method, if you don't know the starting point, then that's not an appropriate method. So for example, you could design a controller that with poles that yield a fast response, but you could end up requiring a lot of power from the actuator. And that requires an expensive device, and so that might not be feasible. Or if you don't have a big enough actuator, then you could end up with saturation from your device, and that causes nonlinearity and maybe even instability in the system. The overview or summary of what optimal control is that it provides a gain matrix K. So just like with the pole placement method, we're still using state variable feedback with this gain matrix K, where our control action is the product of K and X bar. And in linear quadratic optimal control, K minimizes a performance criterion V, or cost function, that is a quadratic. Here is that quadratic cost function. V is the integral from t to t sub f of this sum. So the first term is quadratic in the state, and the second is quadratic in the input. Q and R are these symmetric matrices that we're going to work on choosing what their values are. And the lower limit of the integral is the current time, and the upper limit is called the terminal time. This terminal time can either be finite or, most commonly, infinite. Now, the optimal control process, or designing a controller with this method, is similar to that for the pole placement method. And here's how. In pole placement, the desired characteristic equation was the design decision. So after we had done that, then the calculations were pretty mechanical. There wasn't creativity involved beyond choosing what the characteristic equation was going to be. And so similarly for optimal control, determining Q and R is the designer's puzzle. And again, here are Q and R. So it's figuring out what we want these values to be is where the decision-making process comes into play. After that, it's a mechanical procedure to come up with the gain matrix K. In our performance criterion, there are two terms that contribute to the cost of the control. So this is the cost function that we want to minimize, and there are two terms in here. The first is a penalty on the deviation of the state from the origin. So the controller is going to try to drive X bar to zeros. And the second term is a penalty on the control action. We might want to penalize the control action somehow. Here is an example of just looking at the costs. So imagine we have a system with phase variable state space representation, and x1 is the system error. So since we're talking about phase variables, that means x2 and x all the way through x sub n are its derivatives. If our only concern is the error and not its derivatives, then we could let Q take this value, the value of this matrix, and that would give us the result that X bar transpose times Q times X bar is just equal to x1 squared. Now, what if this design led to a control system yielding excessive error velocity? Then we could change Q by penalizing velocity also. So for example, our quadratic for the state could look like this. We'd have a term penalizing x1 squared and also x2 squared. And C is just a weighting term, so we can weight how concerned we are with error velocity versus error. So if C is less than 1, then we're going to be more concerned with error. If C is greater than 1, then we'll penalize error velocity more. And this would correspond to a matrix Q that looks like this. So we have 1, and then C squared on the diagonal, and all the other terms are zeros. And in a similar way, we can penalize the control action U using R. And if we have a single input, then R is just a scalar. Now the relationships between Q, R, and the closed loop behavior are complex. The result of this is that the approach for using optimal control is to choose Q and R, and then we'll compute the resulting K that minimizes the cost function. Then we'll use that gain matrix K in our closed loop system, and we'll assess the dynamic behavior of the resulting system. And if that behavior is not what we want, then we'll just modify Q and R and recompute K and then check the dynamic behavior again. Just taking a little break. So far we've looked at the motivation and a general outline of the performance criterion. Now we'll look at how we solve for the optimal gain matrix K. Here again is the performance criterion. It's this integral, and we can rewrite this where we take out the initial state vector, x bar of t, and introduce phi sub c, which is known as the state transition matrix, and the c subscript indicates that it corresponds to the closed loop system. Now, the state transition matrix is generally difficult to compute, and so fortunately we're not going to have to compute that. We're going to replace all the terms inside the parentheses with M. So this is a symmetric matrix M that depends on the initial time and the terminal time. If we take the derivative of V, we end up with this equation for M, and A sub C is the closed loop state matrix. If we're using the gain matrix K to close the loop, we can substitute A minus BK for our closed loop state matrix, and so we end up with this equation. And again, our goal is to find some value of the matrix K that gives us the smallest possible V. And again, V is x bar transpose M times x bar. And I left off the term showing that this is the initial, this x bar depends on the initial state, and M depends on the initial time and the terminal time. I mean, x bar depends on the initial time. M depends on the initial time and terminal time. Now, working to find K, we're going to skip some steps and just get this equation. So now we have K hat in terms of M hat, and the hat indicates a minimizing matrix. So this K is the K that minimizes V whenever we use it, and so that's related to M hat according to this equation. So if we know the M hat that minimizes V, then we can calculate K hat. If we take this and substitute it into our differential equation, we end up with what's called V-Riccati equation. We've got this first order differential equation that is a sum of linear terms and a quadratic term, and that is a Riccati equation, but in controls it's known as the Riccati equation. Now in general, this matrix M hat, the minimizing matrix, can only be found by numerical methods. But in one of the first of the two examples in this video that we'll come to in a minute, there's an analytical solution for M, or M hat. Now we're going to extend or apply those equations from the previous slide to the steady state scenario, that is, whenever the terminal time is infinite. In that case, the integral for M either grows without bound or it converges to a constant matrix. In the latter case, the derivative of M is 0. So we can use that knowledge and in the Riccati equation, and we end up with this expression for M hat. And this is what we use to solve for the optimal gain matrix K from the equation we saw previously relating K hat to M hat. Now, a word on the solutions to this equation. This equation represents n times n plus 1 over 2 coupled scalar equations. And since they're quadratic, each has two solutions. So we expect to have n times n plus 1 different solutions. Now, we need to know which solution to choose. And we look to the fact that m hat has to be positive definite. So, if m hat is positive definite, well, there is one unique solution where m hat is positive definite, and that gives us one unique k hat, and that is contingent upon the fact that the system is either asymptotically stable or it's both controllable and observable. So if the system, the closed loop system, meets those criteria, then if the original system meets those criteria, then there is one unique positive definite solution for m hat. Now we'll look at two examples to finish up the video. Example 1, where we want to design the controller for a DC servo motor. And we could use theta and omega for the state variables. So we have these two state equations, theta dot is equal to omega, and omega dot is equal to negative alpha times omega plus beta times u. U is the armature voltage. And alpha and beta, we're just saying, we're substituting those for the system parameters. So that depends on the mass moment of inertia of the system, the motor parameters, etc. Now, our controller is going to drive the state to 0, so we want to change these variables. And we'll look at, and also, since we have a servo, we want to get the position to theta sub r, the desired position. So this is our reference position that we want to get the position to. So we can define the servo error as the difference between the motor position and our reference position. And then the derivative of that is the difference between the motor velocity and the desired velocity, which is just the motor velocity omega. So that assumes that we have a constant reference position for the servo. And now substituting this, we end up with the following state equation. We have E and omega for our state vector. So here is x bar dot, and our state matrix, and our state vector, and our input matrix. Now we're going to look at designing a controller for this system when we have this performance criterion. So we've got Q1 squared multiplying the error squared, and Q2 squared multiplying the input squared. So here are Q and R that correspond to that performance criterion. So backing up, we're not penalizing at all omega, we're just penalizing the error and the input. So there's no term here for the error. I'm sorry, for the velocity. All right, we know that M is a symmetric matrix, so we're going to denote the elements of it as M1, M2, M2, and M3. And we can find it according to this equation. We can find the optimal M, the minimizing M, according to this equation, so M hat. And just substituting what we have for A and B and Q, we end up with this for M hat A transpose M hat looks like this, and then this term M hat B times R inverse times B transpose times M hat, we end up with this. Now, K hat is given by this equation, and that now I had to correct something in this slide. I'd left off the R inverse. Okay, but the point is that we only need to solve for M2 and M3 in the minimizing matrix M hat. And now combining all the equations, we end up with these expressions for M2 and M3. And then we apply the knowledge that M hat is positive definite. So we get that M2 is Q2 over beta, and here's an expression for M3. So depending on alpha, beta, and the factors Q1 and Q2, we can solve for M2 and M3. And then from there get the optimizing gain matrix K. And here is K. So we'll look at some numerical examples for this. Say we have a system where alpha is 1, beta is 3, and again our performance criterion is given by this quadratic. Using these values for alpha and beta and Q1 and Q2, Q1 and Q2 equals 1, we end up with these gains K. So the significance of Q1 and Q2 being equal is that we're penalizing equally the integral of the error squared and the integral of the input squared. And here is what the error looks like over time. And so you can see that it's an underdamped second order system. Here are the resulting closed loop poles, and this is the input over time. Now if we change it, make Q1 twice Q2, that means that we're going to penalize the integral of the error squared more than we'll penalize the integral of the input squared. So we would expect that the integral of the error would decrease and the integral of the input would have to increase, because we want to have faster response, means we're going to have bigger input. So here you can see a smaller integral for the error squared, okay, and resulting larger integral for the input squared. And what happens if we really make the penalty for the error bigger? Now we end up with a much faster response and a bigger input. So now our magnitude is 10. Perhaps you couldn't see it on the video, or on this, on the videos. The input here, the magnitude is 1. That's when the penalties were equal. When we doubled the penalty on the error, then our magnitude of the input became 2. And now when we have Q1 equals 10 and Q2 equals 1, the magnitude of the input is maximum at 10. Okay. And now if we change it and we penalize the input 10 times greater than, or the input squared 10 times greater than the error squared, we end up with these gains and an overdamped system. So it looks like this. So you can see that we have a really big error squared integral. It takes a long time for the error to go to 0, but we have a very small integral for the input squared, because the maximum input is just 0.1. One thing that I'd like to go back that I kind of glossed over is that you can see the poles changing. So this has a real part when the gains were equal. We have a real part of negative 1.3, and when we double the penalty on the error squared, we have a real part that's farther from the imaginary axis. So it's transient response is going to be faster. And then here, when we have a much bigger penalty on the error squared, we have poles that are much farther from the imaginary axis, so we'll have a lot faster response. And then here you can see we have the, again, overdamped second order system. The second example is a 2-car train. We've got these 2 carts, and they're connected by a spring, and they have positions x1 and x2. So when x1 is 0, this cart is here. When x2 is 0, this cart is here. And when x1 equals x2, that means the spring is at its normal unstretched length. And we're going to use optimal control to design a controller where we're penalizing the sum of the cart displacements. It really should be the square of the sum of the cart displacements, and then the difference between the cart displacements, which is the spring deflection, and also input force. Okay, so these are the 3 things that we care about in our performance criterion. And here is that resulting performance criterion. We've got x1 plus x2 squared, and then q, which is a weighting factor for the spring deflection, x1 minus x2 squared, and r, which is our weighting factor for the input squared. that corresponds to the matrix Q that looks like this, and R equal to little r squared. Now we have a 4x4 matrix M, and the minimizing matrix is found according to this equation, just as the previous examples. So since this is a symmetric 4x4 matrix, we end up with 10 coupled quadratic equations, so 20 solutions. And the minimizing matrix M is solved numerically. We use numerical methods to solve for the positive definite M hat, according to this equation. Now, if we let Q equals R equals 1, so in other words, we're penalizing the sum of the displacement squared, the spring stretch squared, and the input squared. If we're penalizing those all equally, then we end up with these 4 values for the gain matrix and these 2 pairs of complex conjugate poles. These graphs show the result. The yellow line is the position of cart 1. The blue line is the position of cart 2. You can see that the initial conditions are that cart 1 is at 2, its initial velocity is 0. Cart 2 is at 1, its initial velocity is 0. So here, in other words, here is the initial state vector. And then the red line is the spring deflection. So this is the difference between x2 and x1, or it's the difference between x1 and x2. And then the second plot we show the green line is the input. Okay, so here it is where they're all penalized equally. You can see that the sum of these displacements goes to 0, so the state, and then the spring deflection also goes to 0, and the input goes to 0. Now what if we change that? We'll decrease Q and R, so now we're penalizing the sum of the displacements most heavily, and we end up with these different values for the gain and different closed loop poles. And here is the somewhat surprising response. If you look at x1 and x2, you see that their sum goes to 0 rather quickly. The spring deflection, that term in the integral is not going to go to 0 very quickly, but it's less important according to our weights than is the sum x1 plus x2 squared. So the blue line plus the yellow line squared goes to 0 quickly, so that has a small effect on the integral. And then the input is bigger than the previous scenario. So here is the input where we penalized, or here's, yeah, the input equal to the other terms, and here's the input when we don't penalize the input very much. Okay. And again, this is for the same initial state vector. Another example, now we're going to look at if we penalize the spring deflection heavily, 10 times greater than the other 2 terms. We end up with these 4 poles, and here's the response. So you can see that the position of cart 2 goes up, so this sum has a bigger, we're not so concerned with that integral. What we are concerned with is the spring deflection, so the difference between these two. So they quickly, x1 quickly becomes x2, and again, this doesn't mean that the carts are on top of each other, it just means that the spring deflection reaches 0 quickly. And here is the input. I keep forgetting, so the magnitude of this input, excuse me for all the flipping around, I just forget and want to go back and highlight something. So the maximum magnitude of the input when they're all penalized equally is 2. Whenever we penalize displacement most, the input has a maximum magnitude of, well, greater than 8. And similarly for this case, maximum magnitude around 8. So this is when we're penalizing the spring deflection the most. And now we're going to look at what happens if we penalize the input. So we just want to have a small input, that's our main goal. And you can see that the integrals for the or the sum of the positions and then the spring, and also the spring deflection, they don't go to 0 very quickly, but the displacement, the input does go to 0 very quickly. So it has a small integral. Input squared has a small integral. The maximum magnitude is less than 1. Summarizing this video, we saw that that optimal control enables the designer to prioritize response aspects other than the transient behavior. So we looked at an example of whenever we cared about the error velocity. We looked at examples where we cared about the input magnitude. We looked at, in the last example, we cared about the energy stored in the spring, so the spring deflection. So optimal control enables the designer to prioritize behavior other than the transient response. And again, the process for designing using optimal control is that we'll choose the cost function, or design the cost function, so that is, what are we going to penalize, and then we'll choose the weights, how important is each parameter relative to the others. Then we'll calculate K and evaluate the response, and if necessary, repeat the process. Now, it must be said that linear quadratic optimal control provides an optimal controller for a quadratic cost function. All the examples for the performance criterion or the cost function that we looked at in this video were quadratic. If we had a different cost function that is not a quadratic one, then it would require a different approach for designing a controller.